Hello, I am Blake Batters, and I'm going to present to you the results of some research that I did along with Professor Aspen Olmsted in taking a look at how to improve the CRUD performance on hierarchical data sets in relational databases. And in this research, we are specifically looking at the nested interval model versus the nested set model. Just a quick overview. I'll give an introduction of relational databases, an introduction of the various models and how we would represent hierarchical data in relational databases. I'll explain the implementation that we used for this specific research, the algorithms that we used to create both the models, the results from this passive research, and then some of the future work that we want to do moving forward that we want to look at. This is just an example of hierarchical data, kind of a typical org chart with the CEO at the top, and then you have two VPs and an HR director, and then they have people beneath them. And so just to give an idea of the data that we're trying to represent, it's something that appears like this, where there's a parent that can have many children. With relational databases, they're used to store an incredibly large amount of data, and the way that they store this information is in individual tables, and each specific piece of information is stored in this table as a row, as a tuple, and this tuple can have various attributes based on it, and each column within a row or within a tuple can reference another row in another table or another row in the same table. It's an extremely structured database. You explicitly spell out what data is being assigned where, and so this can cause kind of a challenge when trying to represent hierarchical data that is not necessarily very well structured, and you don't always have the same amount of children, and trying to define it in a way that queries are quick and efficient is a challenge, and trying to structure the data in a way so that creates and deletes are also quick and also efficient is also a challenge. So a method that wasn't part of this research is by having each tuple reference its parent. If it's a child node, then it references its parent, but that's in other research papers that I looked at, the query results of that are very slow, and so I didn't look at that method. I looked instead at the nested set model, which is faster query wise than the adjacency model, which is where the child just references the parent. And so if we want to look at the nested set model using the org chart from previous slide, how the nested set keeps track of where objects are is it assigns each node or each tuple a left and a right value. So we can see right here that if there's only one root node, then the left is 0 and the right is 1. But as we add tuples, we start to increment the left and the right so that the left and the right of a parent node, that range always contains the left and the right of the children. So we add the VP R&D, we can see that the CEO left still remains 0, and if we move down to the VP, then the left there is 1, the right is 2, and the right is 3. So the VP of R&D, that left and right of 1 and 2 is in between the range of 0 and 3. And so that allows us to search for things quickly. And then as we add the software architect, again, the numbers change so that every child is within the range of its parent. As we add the tech manager, we can see the numbers update for the VP R&D and the CEO. When we add the VP of finance and the account manager, again, the right value of the CEO changes. And then finally, when we add the HR director and his child nodes, the CEO value increases and the left and right values are assigned for the different nodes there. And so as we add and delete nodes, we have to make sure that we keep the left and right value of nodes that are affected updated. So this nested set is the first model that I was looking at, and the other one is the nested interval model. And with the nested interval model, how we represent the data in the database is the CEO has a left and right value as well, but it translates more to values on a number line. So for my specific implementation that I used, I created a custom algorithm. The root node spans from from 0 to 1 times 10 to the 35th power, which is the largest value that a decimal in MySQL would hold. And so that's the interval that the CEO has. And when we go to add the VP of R&D, similar to the nested model, we want the left and right value to remain within the value of the CEO. But instead of going back and modifying the CEO's value, all that we do is we give the VP of R&D an interval that is half of the remaining interval of the CEO. So in this case, that's 5 times 10 to the 34th to 1 times 10 to the 35th. And so the VP of R&D gets its left value and its right value from the remaining open interval on the CEO. And then we'll see that as we add the software architect and the tech manager to the VP of R&D, it follows a similar algorithm. We add the software architect first, and it gets half of the remaining interval of the VP of R&D, which puts it from 7.5 times 10 to the 34th up to 1 times 10 to the 35th. That's the interval associated with the software architect. And then the technical manager gets half of the remaining interval from VP of R&D that doesn't have any children on it, which is 6.25 times 10 to the 34th up until 7.5 times 10 to the 34th. And we're going to see that as we add the VP of Finance, the VP of Finance is going to get half the remaining interval, or half of the interval from the CEO that doesn't have any children. And then the account manager is going to get half of the interval of the VP of Finance. And we can see that added there. And then finally, as we add the HR director, the people manager, and the IT manager, we'll see that the HR director, again, gets half of the value of the CEO. The people manager gets the right half of the HR director. And then the IT manager is going to get the right half of the remaining interval of the HR director. And so as they get added in, this is kind of how they would appear like as on a number line. And so like the nested set model, we have the advantage of the queries are very quick, because all that we have to do is check the left and the right of each node to see if it's in between the specified left and right value of the category that we're searching for. And so that allows us for faster queries. And when we're adding new nodes, we don't have to go back and change any values. It's able to determine its value just based on the numbers that are already in the system, and we don't have to go and change anything when we're adding or deleting anything. So that's the nice thing about the nested interval. And so as a result of that, our hypothesis is that the CRUD operations on data that's structured in a nested interval, again, the one that's represented by the timeline, will be at least an order of magnitude faster than the data structured in a nested set. So whenever we're creating new objects, or whenever we're deleting existing objects, if we don't want them in the structure anymore, or if we want to move them somewhere else, it's going to be significantly faster on the nested interval model than it will be on the nested set model. So while this is our main hypothesis, we also want to make sure that the query speed is not severely hampered in the nested interval model, because we don't want to sacrifice the query speed just to have quick create and destroy operations, because then that negates the whole purpose of having the data structured in a hierarchical manner, because we want to be able to quickly query and figure out what are subchildren and what are leaf nodes of the different nodes that we have in the tree. And so when it came to the implementation of this, Dr. Olmsted and I decided to just use a development laptop that we had. So it was running Windows 10 with an Intel i7 CPU clocked at 2.7 gigahertz at 16 gigabytes of RAM. We installed LAMP server 3.0.6, so just a server that uses Apache, MySQL, and PHP. When we created the trees, so the tree and the nested set and the nested interval both had 5,501 nodes. That gives us one root node and then 5,500 children. And so each node would have 4 children off of it. That was just the data structure that we decided to use. And so here we can see on the left there is the algorithm for adding a child to a node in the nested set, and on the right there is the algorithm for deleting a child, or excuse me, deleting a node from a nested set. And what the algorithm for adding is doing is first it's passed in the parent ID, and so it gets the right value of the parent ID, and then every node. So the first update changes the left and right value of every node that has a left and right value greater than the right value of the parent. So the first update goes and updates the left and right value. The second update goes and updates the right value of every node that only has a right value greater. So these would be parents of the passed in parent ID, only need the right value updated instead of the left value changed as well. And then we add the new node with its correct left and right values as a child of the parent ID that we passed in. And then for deletion, the first thing that we do is we delete the specified node and all of its children. So we pass in the ID and we get rid of all the children. So any node that has a right value less than or equal to the right value, or a left value greater than or equal to the left value. So we get rid of all those. And then similarly to the addition algorithm, we need to update every node that's to the right. So the left and right value need to be decremented by the amount of nodes that were deleted times 2. And so the first update goes and does that. And then the second update updates the right value of any parent nodes. So any node that had as children the nodes that got deleted, only its right value gets updated accordingly. And so that's what both these algorithms are doing. And then with the nested interval implementation, we only had to implement the adding algorithm, because the deleting algorithm, all that we have to do is delete the specific node that we want, and then instantly the children just become children of the node that got deleted's parent. And so here we can see the addition algorithm, and basically the only thing that really matters is if the node that we're adding this as a child of already has a child. So that first is if it has a child, then we have to calculate the remaining part of the interval based on the most recent child's left value and the parent's left value. So the most recent child's left value will kind of determine our right value. The parent's left value will, when combined with the child right value, will help us determine the range of our interval. And then if there is no child and this is a leaf node, then all that we have to do is take up half of the interval of the parent, and that determines what our left and right values are going to be for this specific node in a nested interval. When it came to compare these two implementations, the tests that we used were an insert, a delete, and a query. For the insert and delete, we had to do a best case, an average case, and a worst case for the nested set model, because based on where the node is in the tree that we want to delete, that's going to determine how long it takes, because the further left in the tree a node is, the longer it's going to take, because all the nodes to the right have to be updated once that node gets inserted or deleted. So we're going to see 3 values for the nested set testing. With the nested interval, we were just able to pick whichever node we wanted because they were all going to be the same, since we didn't have to go and update any other nodes. And the query that we used was selecting all the children of the root node. So just a query of selecting every node that had a left value and a right value that was less than or equal to the parent's left node or right value. We were able to use that on the nested set and the nested interval. There is no best case or worst case for either model. It's just the timing is reported there. So here's the results that we found. For the nested set, the insert and query took 0.1 seconds. So all these values are in seconds. The worst case was over 1/10 of a second. The average case was just over 0.05 of a second. And then the best case with the nested set was comparable to the average case of the nested interval. The query speed, so again, we only had one value for the nested set here. The query speed is actually faster, about 2/3 as fast for the nested set as it is for the nested interval. And so some conclusions that we can draw from this is that the average insert time for the nested interval model versus the nested set model, it is decreased by an order of magnitude. And the same holds true for the average delete time, that we save an order of magnitude in the time that's decreased. But this does come at a cost of the query time being increased by about 50%, just because we're doing decimal comparison instead of just integer comparison. And so the nested interval model is extremely useful for hierarchical data that's going to get destroyed and created in real time. So if you're dealing with stock market, or if you're dealing with another type of volatile data, then the nested interval model is going to be advantageous because of the time value that it saves. And so some things that we're hoping to research in the future is comparing our specific algorithm with a dyadic interval model and a Fourier function interval model that were proposed in some research that we found. And so we want to compare the performance of the algorithm that we came up with to these two models, and even in more than just creation, update, and deletion, but for sustained operations, to see how long it takes for them to remain intact and remain usable. For example, one issue that can come up is running out of floating point precision, and so seeing how long each of these models can go before you have to kind of reset the numbers that are being used as an interval. So that's what we're hoping to do in the future with the research that we're working on. Then here are some of the papers that we used as a reference. So thank you very much for your time.